We will hear now a series of short presentations, and afterwards there's time for the Q&A session. If you have any questions, please post them in the chat so that we will come back to them afterwards. And of course, we invite you to ask questions in the Q&A session. We look forward to discussing with you. And first, we will start with an introduction of the IEA Technology Collaboration Program in which this Annex project was carried out. And it's my pleasure to introduce Caroline Haglund-Stignor. She's Focus Area Manager for Energy Efficiency at Rist and Assistant Manager of the IEA Heat Pump Center. And Caroline, please share your slides.
Thank you, Veronika. If you stop sharing. Yes. So do you see my screen well now?
Yes.
Yes. So thank you for the introduction. Yes. My name is Caroline Haglund-Stignor, and I'm working for the Heat Pump Center, which is the program office and the communication center of the IEA Technology Collaboration Program on heat pumping technologies, which is Annex belongs to. And what is the Heat Pumping Technologies TCP? It is a collaboration program that's been running already within the IEA already since 1978. This is an international framework of cooperation and networking for different actors working in the field of heat pumping technologies. And it's a forum for exchange of knowledge and experience, and it contributes to technology improvements by performing research, development, demonstration, and deployment projects. The TCP has 20 member countries around the world. You can see them here. And the countries that have joined most recently are Czech Republic, Ireland, and Spain. And we have member countries from 3 different continents on the globe. Within the TCP, we work with heat pumping technologies for heating, cooling, air conditioning, and refrigeration, and which covers applications in residential and commercial buildings, industries, thermal grids, and cities and communities, and also in other applications. And here is the little bit of the organization of the HPT TCP. We have the main activity within the TCP is to perform those international collaboration projects, which we up to now call annexes, where knowledge are elaborated. And the Heat Pump Centers is the program office and communication center, and then all decisions are taken by a board, the executive committee, which has representatives from all the member countries. And in many of the countries, there are, in addition, national teams. And the Heat Pump Center, we work with dissemination of information and communication. So, for example, we publish the reports from all the projects, the annexes. We publish 3 times a year an electronic magazine, and every month a newsletter. We run a website, and we're active on social media, especially on LinkedIn. And then we work with program support to support the board and the project leaders, and we also work a lot to stimulate that new projects are started. And next week we will organize a national experts meeting with this purpose, and we give support to IEA publication and also work with other outreach activities. And just in the end here, this is the recent number of the most recent number from the HPT magazine that was published a month ago, where we reported from the most recent conference organized within the TCP, the conference that took place in the 14th IEA Heat Pump Conference that took place in Chicago in May. So if you're interested in reading this, please visit our website, where you can find the electronic version of this magazine. And if you want to subscribe to the magazine, we can send you the link, and we can see that many of you who registered for this meeting have also asked to be a subscriber of the magazine. Next issue will be published in the beginning of December, and it's about heat pumps in district heating and cooling airports. And here are contact informations for me and my colleagues who work within the TCP. So thank you.
Thank you very much for the overview on the technology collaboration program and all the possibilities to publish and to follow the information that is created there. Before we dive right into the contents of our work, I will give a brief introduction of the Annex project itself. So I'll just share my screen. Should be this, yeah, should be here right now. So as we heard, the projects in the heat pumping technologies program are called annexes, and our annex is Annex 56. And the topic is digitalization and IoT for heat pumps. We started this project in January 2020, and we finished it by the end of last year. And we had 7 European countries that participated in this collaborative effort. From Austria, it was TU Wien, University of Applied Science Burgenland, the Austrian Academy of Science and AIT. The Danish team was the Danish Technological Institute, Technical University of Denmark, and Energy Machines. From France, there was EDF participating. In Germany, Fraunhofer Institute for Energy, Solar Energy Systems, and RWTH Aachen University. Participants from Norway, from SINTEF, but also from Switzerland, Hochschule Luzern, and two participants from Sweden, RISE and KTH. So this was the group that was working together, and of course there are many people behind these organizations. This is a list of authors. All these that are listed here have contributed to the reports that we will also publish today on the website. During these 3 years of project work, there were many more participating. And I also like to take the opportunity right now to thank you all for this fruitful collaboration and the effort that you put into this joint project. It was really a great pleasure to work with you, and I look forward to share all the results today. In the IoT Annex, we have explored the opportunities and challenges for connected heat pumps. We assessed the state of the art and the state of digitalization in the participating countries. We analyzed more than 40 different examples of IoT applications for heat pumps, and we will introduce a couple of them today. For all these examples, we have created fact sheets that you can access on the Annex website. You have the link below, and we will also post it in the chat. The IoT Annex has a broad scope. We looked on heat pumps for households, but also on heat pumps for industrial and district heating applications. And we had dedicated tasks on interfaces and protocols, another one on analysis, data analysis, and the fourth one on business models that we will introduce today. All this information is available on the Annex website, where you also find the reports, and you can access the website via the link or also using the QR code that is shown here. So much for the general introduction. I will stop sharing now, and I will hand over to Davide Rolande. He is a researcher at KTH, and he was also responsible for our work in task 1, and he will show us now what you will find in the report on the state of the art. You're still muted, but we see the slides.
Good morning, everybody, and thank you, Veronika, for the introduction. I'm Davide Rolando. I'm a researcher at KTH, Energy Technology Department, Division of Applied Thermodynamics. And here in this short presentation, I give you an overview of the content of the report of the task 1 of the Annex 56 on the state of the art of the digitalization and IoT for heat pumps. Well, in the report, we start with the state of the art and a little bit of history, if you will. I propose here one of the first definitions of Internet of Things that is more or less elaborated, but I think it's important because it remarks the shift of paradigm between an internet of data and people, where the communication was intended mainly between machine to machine and person to computer, and the paradigm shift it broadens the definition of communication devices into things, more in general. And this shift of paradigm led to a proliferation of communication protocols and consortia that, of course, also open a wide range of opportunities for companies, interdisciplinary companies. But also it led to some level of uncertainty to what to invest on, what to adopt, what should I use for my system and why, and will this be the communication protocol of the future. And we give an overview of all this in the report, going through a little bit of the history and the main characteristics of even old communication protocols that have been improved along the way, like Modbus, to mention one, and other more web-based session layer protocols like AMQP and MQTT. But to put all this into the context of heat pump systems, then we collected a number of use cases, in particular 44 use cases that are classified in two types, products and services and research projects, and they are categorized according to these 5 categories. And we elaborated one fact sheet per use case according to the framework that is here represented in this schematic overview. And as Veronika mentioned, you find all these fact sheets available in the IoT Annex website, and there you can browse the use cases by type, by country, and by category. Moving on, then we have contribution from a few countries. For example, we have the market report from France. There we have the summary of a study that is called the Heat Pump of the Future, Smartness and Connectivity. And there you have some overview on a couple of definitions of what is a smart heat pump, depending on the context. And it's an interesting reading in my view. And this is a summary of a study that was promoted by the French Heat Pump Association. Then we have the results from a survey that was run in Austria. The survey consists in 50 questions that were circulated by the Austrian Heat Pump Association, and a total of 16 companies participated in the survey. And here you see an example of the results that is related to the motivation to introduce IoT products in heat pump systems. And here you see that the highest ranked motivation is, for example, customer loyalty and service improvement, and the possibility of enabling new business models. There are also challenges that are clear from the survey results, for example, related to data security, data protection, especially the lack of data management guidelines. The increased system complexity because of IoT infrastructures, and connected to this, the availability of qualified personnel. These results are somehow consistent with the expert interviews that I ran in Sweden, where I interviewed heat pump manufacturers, IoT companies, associations, and consultants. And there it was clear that, yes, IoT definitely gives opportunities like enabling innovative business models and advanced solution for predictive maintenance. There are also challenges, like, again, the lack of guidelines and the need for demonstrators. And also consistent with the results of the survey in Austria, the first ranked answer regarding the motivation for introducing IoT products was the reduced operating cost in this case, but consistent with the Austria survey, the service improvement was one of the picked main motivations. And with this, this is just a quick overview. I would like to thank you for the attention, and I take again the chance to thank for all the contributors to task one. Of course, this was a collective effort, so thank you all for the collaboration.
Thank you very much. So you see there's a lot to explore in this report on task one. And we will dive now right into these examples that we have collected. So we have heard 44 in total, covering research projects, products and services related to IoT and heat pumps. And the Danish team contributed the most examples. So we have now 23 examples from Denmark. Congratulations and thank you for this valuable contribution. And we will now hear about 3 of them, presented by Jonas Lundsted Poulsen from DTI, Danish Technological Institute.
Thank you, Veronika. Hopefully you can see my screen now and hear me.
Yes.
Yeah, so as Veronika just mentioned, I would like to shortly show you 3 of these different case examples from Denmark. So what we actually did in the beginning here in the Danish group of the IoT Annex was to make a review about the state of digitalization and IoT for heat pumps in Denmark. And we actually ended up having 23 different case descriptions, and it's quite broad, what they cover. It involves both product and service suppliers, and also different R&D projects being carried out within this subject. And you can see they're listed here on the left-hand side. And as I think I already mentioned a couple of times, you find them on the on our webpage, where you can dig a bit more into them and see a bit more detail than we have time for today. But basically, it's being collected in some 2-3 pages, which gives a good overview of the different cases. But yeah, let me explain shortly here the first case. So this is from Energy Machines, which is also directly a part of this IoT Annex. They have created this tool called the Energy Machines Verification Tools, which is a combined solutions which both include hardware and software, where they have a thermodynamic model of the heat pump. They are collecting data from the system, and then they have this API, so an interface and a dashboard where they can give a quick overview of the current performance of the heat pump. And I think one of the key features of this is that there's really a big transparency between the performance of the heat pump between the supplier and the customer. And that's quite important in a heat pump, because the conditions are changing all the time with different, when the surrounding conditions are changing a lot, it's nice for the customer to know that the heat pump is doing what it should be. And then just to highlight a few things, data security is has a lot of focus in this solution here. So Energy Machines are using encrypted protocols like TLS and HTTPS when exchanging this data. And then the data is really provided in real time. So data is being collected every minute, and also the results from the modeling and so on is being updated every minute. And then moving on to the second case I would like to talk about. This is from an R&D project called Digital Twin, which has focus on digital twins for large-scale heat pumps and refrigeration systems. It's a project we are also participating in here from DTI side. And what we have focus on is to look at some different services we can imagine there is around a digital twin for a heat pump. And just to show the concept for this, if you look at the figure here on the right-hand side, we have a lot of data flowing around between the physical system and the virtual system, and we can then analyze all this kind of data we get, and also get additional data from the different environment, the price signals or weather forecast, and then we can feed them into some different services. And in this project here, we are talking mainly about 3 groups of services. We have as I explained here on the left-hand side, we have the system monitoring, which is about benchmarking and validity checks. Then we also have the fault detection and diagnosis, where we can learn something about the system and then maybe provide some early stage warning in order to do predictive maintenance before there is an error. And then we can of course also use the data for optimizing the system operation. If there are some set points that can be changed to a more favorable point, we would of course create some new data, and then we can collect that again and then make a continuous set point tuning. And then I just wanted to highlight 2 examples from this project here. They are coming from, both of them from, we have some dynamic models of these different heat pump systems. It's some district heating heat pumps in the megawatt scale we have here in Denmark. And if you look at the figure on the top left side, it shows COP and heat transfer rate over the course of 7,000 seconds, so a couple of hours. And what we then do is that we suggest, based on the operating conditions at 3,600 seconds here, we suggest, okay, we have this COP now, but if you go in and change a compressor speed, our model would predict that the COP would increase from around 3.1 to 3.2 when it reaches steady state again after some hundreds of seconds. So that really creates the basis for going in and having a model that can support how we should change these set points. And then if you look at the bottom figure here, this is an example from a system which is really prone to have a lot of fouling. And if we use some adaptive model-based monitoring of this, we can go in and see all the time, okay, what is the benefit now if we make a SIP, so a cleaning in place. And in this case here, you can see, depending on what day it is, okay, maybe the COP could increase from 4.1 to around 4.6. And then you, of course, know the cost of a SIP, but then you can determine if you want to do that now or it's better to wait. Then the third example here, this is from Energy Lab Nordhavn, another R&D project that was carried out here in Copenhagen a few years ago. In this case here, there was a lot of focus on the heat recovery unit, which was integrated into a refrigeration system, which could then supply the heat to the local district heating network or the building itself. And in order to do that, you can see I tried to describe here on the bottom how the different data is being sent around in the clouds. There, of course, needs to be some electricity prices and heat prices being collected in a cloud, which is then sent to some optimization algorithm before it's being pushed down to the real controller of the refrigeration and the heat recovery unit. In this case, it was Danfoss making this. And some of the key results here was that it really showed that in order to make this a good robust solution, you need to go in and adapt the gas cooler pressure in the refrigeration system. And there was also some studies made about what happens if you increase the evaporator capacity. And it actually turned out in this case here that the supermarket could have a payback time of 3 to 4 years if they implement a solution like this. So that was a quick dive into 3 cases, but please check out the homepage for a bit more details. All right.
Thank you very much. We will use the digital twin project as a connection to our next task, and that one is on interfaces, platforms and protocols. It's my pleasure to introduce my colleague Reinhard Jentsch. He's research engineer at AIT and he was the leader of task 2. So please share your slides and show us everything we've learned on the interfaces, protocols and platforms.
I switch back. So I think now you see the right view. Okay, thank you. So task 2 is about interfaces and platforms and protocols. So basically this means everything that provisions communication and processing capabilities of a use case, of a service or of a feature, of a IoT feature. And as we already as Davide already showed you, it's the vast amount of IoT technologies we looked at task 1. So all the protocols, all the technologies, all the services. So how can we focus back to what's relevant for heat pumps to not get lost into this topic? So therefore, we decided to again look at specific use cases that we can group together and then find commonalities, common challenges, and common solution strategies, how the problems were solved in these specific use cases. And also we introduce another concept about how we want to look at different features or services. So this is basically an approach that may be familiar from other concepts. So there is this plan to check, act in concept in quality assurance, or observe, orient, decide, act in adversarial environments, for example, military. So here we say, okay, for each service or IoT feature to create or add value to something, it has to go to a cycle of these 4 stages. So we acquire the data, we process the data, and we make some kind of inference or insight out of this data, and then we make an action based on this insight or inference. And this actions is what creates value. And you also find our task structure again in this concept. So basically, task 3, from which we'll be here later, it takes the second quadrant. So we come from data processing and make some insight inference. And then in task 4, when we talk about the business models, we take our insight of the data, we do some action, we provide a service, and then create value based on it. So we take it from here to there. And task 2 is basically the framework. So what do we need to enable all these steps that are necessary for us? And one example that fits perfectly to this cycle structure is, of course, the digital twin with a twinning cycle. Here we looked at 4 examples that thankfully 2 of them were already presented. So this is the energy machines from Denmark and the digital twin project from Denmark. And we have the digital twin project from Aachen, what we also will hear later. And from Austria, we have an example of a digital twin used in heat pump testing, where we can predict certain stationary testing points ahead with using the model, the digital twin of the heat pump. So what are the challenges we saw in these projects, and what solutions were applied? So as you saw in the presentation from Jonas, there are quite different digital twins in this project. So they can be on a very low scope and fully automated as part of some control systems, some PLC, up to a very higher order where there can be part of some business logic and have seasonality effects and all that. So very different timescales, very different requirements to simulations and data, historical data, amount of data, and all that. So what does that mean? You need something to orchestrate and facilitate all this data. So what we saw in many of these examples is the use of data brokers, preferably MQTT system. And you want to automate all of these digital twins, so make this easy to use and scalable. So we saw Docker containers, we saw FMU units to separate the modeling from the simulation environment, and also the use of frameworks. So some frameworks that really make it easy to use to connect the modeling with the data. So this is example of we see in energy machines, and also is part of the digital twin project from Aachen. The next example is connected, or the next group is connected heats in connected heat pumps in building automation. So now the heat pump is per definition a part of a connected system. So the challenges that come up is the heterogeneity, the complexity of the whole system. We can get a huge amount of data volume. And of course, data security and protection becomes even more important, because now we often deal with personal data. And also there's the questions about level of control. If you have a complex system with different participants, so not only the heat pump, but we can have automated shutter blinds and other systems, where do we control to find not the good control for one system, but for all of the systems. And we have a lot of proprietary protocols that have to work together. So what, from the technical solution standpoint, we see the usage of gateways, a lot of gateways to go from one protocol to a common communication protocol. And we see semantic data representation in those both examples, from which we will also see one later today. BACnet was the choice to do this. And the next group is heat pump in grid services. So here the service provider is per definition an outside entity. So it's not something you do in your own house. It comes from an outside service provider. So, and of course, the heat pump is part of the power grid, so this makes security very important. And also we see a lot of retrofit, and all of the components have to work together. So, and also we have all different levels of user engagement. So we see the layman user and a professional service provider on the other hand. And so what is important here? So in these projects, the one is from Sweden. So we see the attempt to define and standardize interfaces that should enable plug and play capabilities and provide all this, solve all these challenges. And the other project, the TICO project from Switzerland, is basically an all-in-one solution where you can buy this TICO box. It gets installed at your house, and the connection is all in one system. And so retrofitting is not really a category by itself, but it's part of all other use cases. So the reason for this, heat pumps can be in use up to decades. So, and the requirements change over this time. So what seems a good hard and software back then doesn't need that mean that it's 10 years later. And we want to introduce additional features and capabilities. So again, the challenges: legacy protocols, proprietary communication capabilities. So the structural conditions on site is also an issue. And if we retrofit, we also want to maintain the core functionality usually. And so some solutions we see a lot is, of course, wireless connections. There's a lot of technology available. So there's Wi-Fi, there are the GSM networks, and there are the low energy protocols, LoRa, Zigbee, and all that. And we often see a layered approach. So there's a clear distinctions between the field level, where about the heat pump operations, then there's a gateway, and then we see some translation to an more advanced IoT protocol, and then integration in the IoT and cloud and all that. So a quick summary. That I want to underline with a graphic from the survey we did in Austria is basically sensors, hardware, and software. This is available, and the problems here are solvable. It doesn't mean there are none, but they are solvable, and they are part of this whole IoT topic. So the heat pump world is not alone here. And the other more pressing issues are the increasing complexity of the systems, the retrofit aspects, the heterogeneity of all the protocols and platforms, the security. So we always come into, we often come to privacy data. And this means a high integration effort. So what helps is defining standards and going on forward here, provide frameworks that make it easy to use, to create digital twins, to use them, to make predictions, to visualizations and all that. And what also really helps is semantic presentation to provide more plug-and-play capabilities. So, thank you. Back to you.
Thank you very much. We will now hear more details on the SAP Lab that was shown as one of the case studies on heat pumps in building automation. This will be presented by Kristian and Skeie from SINTEF. So please share your screen.
Yes. So I'm a researcher at SINTEF, and I will present the SEB laboratory and building automation and control, which was one of our topics in the report. So this building is a laboratory, but it's also an office and a university building at our campus in Trondheim in Norway. And it was built 3 years ago as a zero-emission building with high ambitions for the construction phase and operational phase, and so with all the material that went into the building. And it's an area where we can develop new materials and technologies and test them. And the advantage is that it's also our office. So I sit here where you see the little circle. Building automation systems, of course, is nothing new. What's new is that there is a trend towards more IP-based communication, and you have more all-in-one devices. But in this building, we still have like a traditional building automation network, which is closed from the outside world, and we use automation controllers to speak to devices that use many different protocols on the field bus level, and then we have gateways, and so it is a layered approach, as you can see here. The energy concept of the building is there is PV to offset the emissions from the materials in the construction and the electricity that we have to buy from the grid. We're also connected to district heating, and we have 2 air-to-water heat pumps in this building. We also have an innovative energy storage system, and we are investigating energy flexibility and integration with the campus local district heating and electricity ring. It's a bio-based biowax that operates around 35 to 40 degrees. So this is a low temperature system. And as part of the commissioning of the building and our participation in the Annex, we had several small projects where we have looked at ways to integrate the data from the building and build services for the optimization of the set points. One colleague looked into predictive maintenance, and what I will talk more about is the system monitoring and diagnosis, and how we did that by integrating the sensor data and some models. Yeah, so like I said, it's this layered architecture. The meters that are relevant for the heat pump are on different protocols. We have the heat pump, which is Modbus, electricity meters there are also Modbus, and then heating meters that are MBus, and these are integrated with a Siemens Desigo PXC, which is an automation controller that then it makes the data available over BACnet, and then we pull all the automation controllers and the room controllers in the building, and we have a custom application that we call BACnet to Influx, which then integrates all the data from these automation controllers into the time series database. But what I will say is that we also integrate data from other third-party sensors and external web services like price signals and sort of external APIs, so you can see here. And what we also looked at in this application was how we could use that time series platform and in the development of applications. And we found that it's very useful to write back the model results, for example, to the same database, in the way you can then analyze and interpret the data. And that we could also write optimized set points back to the system, either by reading them from the database, so the database then becomes our gateway back to the closed system, or directly with another custom script that we call Backforsk. And both Backforsk and this BACnet to Influx are based on a Python library called Back0. Yeah, one of the challenges, of course, the one I will outline here, is how we can represent and connect the various data sources and use some form of semantic enrichment of the data. In this application for the heat pumps, we built some models from design documentation, and we were able to automate that process from the simulation tools that we used in the design process quite well. But there is still a challenge in interpreting the sensor data. We have metadata storage in the time series database, which is just key value pairs, basically. So there's no structure to it, but it's built around a labeling scheme that is used a lot in Norway called the Statsbygg TFM. And you can see an example of it here. So we interpret that, and since the control delivery and the commissioning of the building then was following this standard, it means that all the BACnet devices also have embedded these codes in their names, so we can interpret that. But at the moment, we are not using that fully. We're using a spreadsheet where, we read that in together with the BACnet messages. But that's also a way for us. We see that sometimes you might have to have like a translator, or there could be errors in the codes. So we use that spreadsheet then to keep like assure. And from that information, we can build queries, and we can explore the data with these tags in Influx. What we would like to do next is to look more into how we can automatically interpret these tags from BACnet. And that's also important when we take this to other buildings, of course, so that it's easier to set up and reuse. And what I find interesting is that there are developments like this NREL building motif that is going to make that a lot easier to build semantic models like a bricks model, for example. So some lessons learned. Well, we found that it has a lot of value to write back the model results into the same database for analysis, and we could essentially also write set points back and read them from the database, since we're not really in, most of our applications are more near real time than actual real time applications, I guess. So the delays are not so important. This is minute-based data, by the way, and that we want to explore new ways to enrich our data. And we are developing these two packages, BACnet to Influx and BACfirst more, to have more predictability. So, for example, with how we buffer data if the database is down, and we also are looking at developing more specialized APIs. Getting data out of the building is easy, but of course, when you want to take control over certain parts, then security becomes even more important. Here, if you want to see more, then there's a webpage, seblab.no, and you can go here on more data and explore some dashboards. Thank you.
Thank you. Thank you very much, and also thank you for the outlook. What's coming up on the SEB laboratory in the future. So now we have seen how heat pumps are connected, how data is collected, and now we will move on to a very important aspect, data analysis. How to make use of all this data and how to create a service or a business from that. Tim Rist is a researcher at Fraunhofer ISE in Germany, and he was managing task 3 on data analysis. So please share your slides and go ahead with your presentation.
Thank you, Veronika. So, and also welcome from my side. I'm very happy to present you a rough overview on the results from task 3. So the task 3 was about data analysis. So we already saw some examples where use cases apply data analysis methods. So why data analysis? Broadly speaking, data analysis tries to leverage the data collected from an IoT field devices to gain new insights and optimize operation. So like in this small example where we fetch the data in the field as time series data, like we saw before, connect it with some semantic data and then apply some sort of data analysis like for detection diagnosis to get results, and then there might also be a feedback loop through person on automated one. And in the task 3, we try to discuss the different kinds of data analysis aspects from the national projects. From that, we collected the different use cases where this kind of data analysis methods were applied, like we saw before in the different examples. And we did a categorization of these data analysis methods to bring together all these different use cases on the same page. And then we also discussed the boundary conditions for the applicability of these data analysis methods. Just like we saw in the previous examples where we find the difficulties in actual application of these methods. And from that, we created the task 3 report, which has the shown contents. So basically, it tries to give some best practices on pre-treatment of data, which is really important for the application of these methods. All this coming from the insights that we found in national projects and the use cases. And then also the usage of data models, metadata, and building information modeling, or so-called BIM. Like we saw before, it's not only sufficient to look into the time series data itself that we collect in the field. We also have to look into the semantics of the building, of the appliances, the heat pump, and the semantics of the data itself. So what kind of data we're looking at actually. Then in the report, we also give a short overview on the applicability of data analysis methods in buildings and abroad, because as we also heard in the task 1 before, these buildings are really heterogeneous, and which makes it hard to apply data analysis methods in this field. And then we also given a short overview on the specific use cases in the annex that are targeting certain data analysis methods, where we looked into the used data analysis methods and also their specific IoT aspect. And from that, we derived a categorization of the analysis methods. So from the more coarse categories to more fine-grained one. So the coarse ones are the ones that were already introduced in the presentation on task 1, where we look into different applications of IoT technology, like heat pump, operation optimization, predictive maintenance, and so on. And then we go a bit deeper and look into the target that is targeted for through a specific data analysis method. So here, while in the first category, we could use different methods to reach a certain goal, here we're looking into why a certain method is applied. And then we have the unification of the data analysis methods itself. We then derived from that more detailed comparison of the different use cases in form of a table. So here it's only as an excerpt. You can see the full table in the report, where we did a comparison of 16 of these 44 use cases, because we had more details on these 16 use cases, where we applied this categorization we saw before, so concerning the different data analysis methods, but also we look into the use of specific kinds of models. So be it data-driven models like in machine learning or physical simulation. And so then we also apply this categorization of the use cases in this table. So with that, we try to derive a humble hint on the applicability of certain data analysis methods for a certain use case. So the hope would be that when a certain use case arises, one could or have some orientation from the work in this task 3 report. Yeah, with that, I'm already done with a short overview of the task. Maybe we find some time later for further discussion. And I'd like to thank you for your attention and also all the contributors to the task 3 report. Back to you, Veronika.
Thank you. So we will hear now an example for data analysis. We will have a closer look on fault detection and diagnosis that was already mentioned before. And this is a presentation given by Tim Klevik, researcher at the Institute of Energy Efficient Building and Indoor Climate at RWTH Aachen University.
Yeah, thank you, Veronika, for your kind introduction. Good morning and welcome from Aachen. My name is Tim Klevik, and I work together with Kristian and Stefan Göbel in the field of the experimental investigation of heat pumps and refrigeration cycles. And in the next few slides, I want to give you a quick overview on the experimental infrastructure and the methods we use to detect and analyze fault behavior. So I think most of you already are familiar with the so-called Urban Energy Lab, which was part of Kristian's thesis. So he designed this test environment where we can conduct experiments under safe conditions. So especially when it comes to the usage of flammable refrigerants. And we're not only able to control the system, but also to connect and investigate the behavior on a whole heat pump system and heat pump components. So for that, we have a compressor test bench. We can look at the expansion valve and, yeah, as I said, to the whole system. Each of these systems use its own PLC so that we can access and control it, but they also communicate using the ADS protocol of TwinCut and write the measurement and control data to the influx database, where we can access it using automated Python scripts in real time. So this air-to-water heat pump test bench was part of my master thesis back then. Yeah, and back then my main motivation was to investigate the behavior of flammable refrigerants. There was a little shift, so I realized what I can do real good is to emulate different faults and so investigate fault behavior. Back then I designed it working as a monoblock system, so the outdoor unit holds the refrigerant cycles where we can access every component of the heat pump. So when we look on it on a PI flowchart level, we see the refrigerant cycle holding the four main components like the compressor, the heat exchangers and the expansion valves, both for respective heating mode and cooling mode, which we can switch using a four-way reversing valve. And you also see a lot of measurement technologies. So in blue, the pressure sensors, in red, the temperature sensors, and in yellow, Coriolis mass flow sensors, so that we can calculate each state of refrigerant and at any location of the refrigerant cycle, and then go there and to modify the components or to add mechanical faults to the system so we can analyze the fault behavior. So the basic faults are, we can look at fouling of the heat exchangers. We can emulate it by clogging it or reducing the fan or pump speed, and we can vary the amount of refrigerant in the system. So we can look at charge variations and migration and how it impacts the system and how it can lead to over or undercharge characteristics. Because we also use the density functions of the Coriolis sensors, we can have a look at oil circulation characteristics, which can lead to other faults. Yeah, and as a use case, we can look at the typical evaporator fouling, which cannot be detected as a hard fault. So a hard fault would be simply detected by undergoing a certain set threshold, but it's like more a soft fault. So clogging the evaporator stepwise, like here, leads to impact the suction pressure and temperature, which then can lead to a reduction in efficiency. So we can also emulate it automatically by reducing the fan speed and therefore reducing the airflow and the capacities, like covering the lid as well. So for the detection of this behavior, we need more complex algorithms. And together with Sebastian Borges, I tried using artificial neural networks for this, and we followed two approaches. One would be we train the data of the fault-free as well as the faulty behavior. So we know about specific faults like the evaporator fouling and its impact. And then we use features which have a very high sensitivity to the fault condition. In this case, the suction pressure and temperature. And then in the operation under the pre-trained data, we can see that the network predicts that there is this specific learned fault. Another case scenario would be we just have fault-free data to train, and then we choose features which have no sensitivity to the fault condition at all and use them to train key performance indicators like the COP. Because they have no sensitivity, the net will then always predict a healthy state, and comparing this one to the real state, indicates not a certain fault, but that there is something wrong with the system. And connecting these two approaches can lead to very high prediction accuracies. All these tests have been conducted under steady state operation until now. Yeah, to sum this up, we use this infrastructure to look at specific faults and analyze the fault behavior to then improve and develop predictive maintenance methods in order to then counteract the shortage in the maintenance and maintenance staff of heat pump systems. At this point, thank you for your attention, and feel free to ask any questions, to contact me, and Veronika, back to you.
Thank you very much. I will use again your last slide as a connection to the next part about the predictive maintenance. Predictive maintenance is one of the business models that we looked into when we did the work on task 4. So I'll share my screen now. I hope it's here. Okay. So we have analyzed 19 examples for business models that are connected to IoT heat pumps. And we looked at these business models in terms of stakeholders, value proposition, and services. And from the IoT categories that we have seen before, we have found business models with IoT heat pumps related to heat pump operation optimization, to predictive maintenance, flexibility provision, and to heat as a service. So IoT heat pumps are already out there in the world, and they are also part of these business models. In the illustration on the right, you see the different phases in the life of a heat pump. So from construction to installation to operation, and all the different stakeholders that can be involved in these phases. In total, we have identified 10 stakeholders, starting from the heat pump manufacturer on the bottom of this illustration. Heat pump manufacturer designs and constructs the heat pumps, sells them, and also offers maintenance services. The component manufacturer designs and constructs components for heat pumps, such as compressors, valves, and heat exchangers, and sells them to the heat pump manufacturer. The next level is the heat pump vendor that sells heat pumps to end users and also offers maintenance service. And then we have the heat pump installer that, of course, installs heat pumps, and they also may offer maintenance service. And this maybe option is shown in this illustration in the lighter color. Then we have different types of users for these heat pumps. Consumers may be both residential consumers or industrial consumers, so they are the ones that have the heat and the cold that is produced by the heat pump. They can also be responsible for the operation of the heat pump, but there are also versions where there's an operator that takes care of that operation. And there's also another option. There are energy service companies, the so-called ESCOs. They offer a service-based proposition for energy, such as contracting or heat as a service. And they buy and operate the heat pump instead of the consumer, and then sell the heat or heat as a service to them. And leasing would also be an example for the service that they offer. And then if it's leasing, then they only provide the heat pump, and the user operates the heat pump themselves. On top of the diagram in green, we have all these stakeholders that are related to the energy system: the aggregators, the suppliers, the power grid, the power system. And aggregators pool a large number of small assets into a large one that can be marketed on the different electricity markets. And thereby they also have an influence on the operation of the heat pump. The supplier, as the name already shows, supplies electricity to the customers, and they do this by trading electricity markets or by producing electricity themselves. And on top, there's the power system that transmits and distributes electricity, connects suppliers and users, And the power system requires balancing of supply and demand, and this is where we find business models related to flexibility provision, to the marketing of changing the energy consumption according to a specific pattern, which is a very interesting aspect of a heat pump, because a heat pump connects the electric world to the thermal world and offers more flexibility options than other electricity consumers. All the new business models that are related to the IoT function mainly focus on the operation of the heat pump that are shown here on the right. And in the report, you also find detailed SWOT analysis, so strengths, weaknesses, opportunities, and threats. So we had a look at the internal and external factors on positive and negative aspects for different pairs. So we always compared the IoT-enabled business model to the traditional one. We did that for predictive maintenance compared to fixed interval maintenance or on-demand maintenance if something is already broken. We did another one for the stakeholders related to heat as a service versus the traditional model that the resident buys a heat pump and operates it themselves. And the last SWOT analysis is on providing flexibility with a heat pump in a pool compared to using a heat pump as an autonomous component in the building on its own. And you find a detailed overview on these strengths, weaknesses, opportunities, and threats in the report. To summarize our findings on the business models, we have found that the value proposition, the main value proposition for the consumers are lower costs, higher efficiency, and also higher reliability of their heat pump system. The new products and services bring important changes to the whole heat pump value chain, so the heat pump and the component manufacturers, the vendors and the installers, because in a connected setting, they have more responsibility for the efficiency of the system than in a traditional business model where they just sell and maintain the heat pump. There's an interesting potential in the connected heat pumps related to the energy system, because for the future, and also already now, we have a strong need for flexibility to compensate for the fluctuating generation of renewable electricity. And with heat pumps, we can also work on sector coupling, connecting the electric world to the world of heating, also making use of different time constants, as thermal systems tend to be much slower than the electric ones. So this is an interesting asset that we have here in the marketing of flexibility. And the last group that we looked at are these ESCOs, the energy service companies. With their service, they help to spread heat pumps in the residential, but also in the industrial sector, because their services requires less involvement of the users, so they don't have to become experts in heat pump operation. They can simply consume the service and have heat or the energy that they need for their building or their processes. And with that, I'd like to hand over once more to Jonas to show us some more examples from Denmark.
Yes, thank you, Veronika. Yeah, so in relation to these business models, I would like to present again 3 different cases which we have collected. And before I do that, I just want to show a figure here where we tried to, all these different cases we collected, we tried to group them in different, we tried to group them, and you can see the different supplier groups we have here on the left-hand side, because we both have manufacturers of the heat pumps, we have aggregators, service providers, end users, and also some people who are just collecting the data. And it was quite clear for us that, at least when you look at the digitalization of heat pumps in Denmark, that there really are a lot of different stakeholders working on deploying this technology. But also, as indicated on this figure on the left here, there's really a lot of errors between who's talking together, and how to do that in a good way is something that for sure the industry needs to have a bit focus on, how the cooperation between the groups should be in order to to harvest all this potential we see in this with this technology. Yeah, but going into some of the examples here, the first one is from the aggregator located here in Denmark called NeoGrid. They have a heat pump controller called Preheat, and you can see some of the components for the hardware set up on the figure here on the left top side. Yeah, and they provide several services. They have both model predictive controls, but I think one of the big focuses on this aggregator-based services for the electricity market. If, for instance, that's what I tried to indicate here in the picture in the left, at the bottom, they have this possibility for doing swarm control of a range of heat pumps, where they can then go in and allow and block the individual heat pump. When they do, of course, it needs to have some. There is some constraints how much they can change, but if you have enough heat pumps, you just change a little bit, you really have a potential for going in and providing some grid services. Yeah, and one of the key focus areas is, of course, that when they have these services here to save energy and reduce the cost of heat, they also want to, at the same time, not compromise the indoor comfort requirements. So they also are collecting a lot of different data, for instance, the indoor temperature of the different rooms and the house, before it's being collected in this in the cloud by their NeoGrid preheat controller. Next example is from Metrotherm. So Metrotherm has a platform called My Upway, and it's actually their own Metrotherm's own version of their parent company NIBE's online service platform called Uplink. Maybe a lot of you already know this platform here, and yeah, they have. I would like to highlight two features. They have one called the Smart Price Adaptation. So again, an example of that they're collecting information from the electricity grid and also the user's consumption patterns, and then they can give recommendations of how you should operate your heat pump without compromising the comfort of the people living in the house. There's also the different service providers. If they connect to this, the service provider of the heat pump, they can connect to this portal here, My Upway, and then see how the heat pump is behaving, and hence avoid any unnecessary on-site maintenance of the heat pump. If it's just some settings they can overrule or change, that's also a big advantage. Then the third example here is from a project which was run a few years ago in Copenhagen again. It's a system operated by HOFOR, so a big district or energy company located in Copenhagen, and they have built a flexible energy system which consisted of, in this case here, primarily three things. They had an 800 kilowatt heat pump, 200 kilowatt electrical boiler, and then a thermal storage tank of 100 cubic meters. And there was made some various modeling of this system, dynamic models again, and linear optimization models. And then the system was also changed physically, so the heat pump, so it in a better way could adapt really fast to changes which is needed if you want to look at the service we are talking about here, which is a grid services. Then you need to be able to provide fast regulation. And I tried to and then the controller of the heat pump was directly integrated with this model, and so that could give inputs how the system should run. And if you see here on the figure on the left here, there's different curves here. The black one is the electricity price, and you have 100 hours here, so you can see that's of course going up and down depending if it's night or day or if the wind is blowing or not. Then you have the heat demand, that's the green one here, and then you have some different orange colors here, and you can see the optimization model was what it was predicting to run the heat pump. That's the yeah, this one, the light orange one. So you can see if the prices are high, okay, then of course you should try and not run the system. And when the electricity price is low, you should really operate the system, and then you put the heat into the thermal storage tank. And then just to put some numbers on what was, yeah, the conclusion in this project was that if they use this more sophisticated, intelligent control, they could reduce the cost by 7%. And if they provided these grid services, an additional 6% cost reduction was seen. So I think it's a good example of how a larger company can actually, yeah, give a good input to the energy system and also save money. Okay, that was my 3 cases. Back to you, Veronika.
Thank you very much. What I especially like about the last example is that it was a large heat pump that was operated flexibly, and I think there are not so much examples for this way of operation. So you find many more of these fact sheets on the website. You can browse through them by country, but also by project or product, and also by the main IoT categories, whether it's used for heat pump optimization, for flexibility provision, for predictive maintenance, for commissioning, or for heat as a service. So you heard a lot of input from our side, and now we have a look at the chat and also to the audience. If you have any questions to what you have heard now, and the group is not so big, so if you want to, you can also raise your hand, open your mic, and ask your question. So maybe to fill the void when you still think about the questions, or maybe our presentation were all very clear. I'd like to announce another webinar related to digitalization that will take place tomorrow. I think there was already the question in the chat whether it's still possible to register for tomorrow, and yes, it is. Registration is back online again. We have seen so many interesting aspects of heat pumps and digitalization in this project, and this is why there's also the interest and the need for a follow-up activity, another Annex project. So if you are interested in joining and also drafting this follow-up project, I kind of invite you to join us tomorrow for another online meeting. It will be an interactive workshop that will start at 9:15. And we will draft together this idea that is, well, basically given here, how to make use of digital services for heat pumps. So in this Annex project, we have explored also a lot of the environment where the heat pumps are operated. We have seen many connections to different markets, to different stakeholders and other things. And now we want to go back to the heat pump itself and look where we can use digital services, digital applications to improve the operation of the heat pump, to create value for the whole value chain when it comes to planning, to integration, but also to operation of heat pumps. So we have already a couple of ideas, but I look also forward to hear your ideas, maybe your research projects that are already established in this field. And if you're interested to join, please register online using this link, but you can also send me an email and I will get you the connection link for tomorrow. And also, we have another look at the chat box in the audience. Seems to be all very clear what we have done today. Yeah.
Veronika, can you put the link to the registration in the chat?
Yeah, sure.
It would be good.
Yeah.
And could you give any hints on the discussion so far? Which area do you want to explore even more in the follow-up project? Where do you see the need?
Yeah, so there are different areas to explore in this field. So first of all, we know from all these studies from the IEA and all this looks into the future that we will see a large number of heat pumps being employed, many different applications. So heat pumps should be the number one technology in residential heating, but they will also play an important role in industrial applications. So we will see increasing numbers, and this will also impact back on the whole value chain. So we need many people who are able to install, to build, to integrate these heat pumps, but also to operate them in a very efficient way. And this is an aspect where digitalization and modeling can really help, where we can facilitate good solutions with the help of models and digital advisors. So I think this is an interesting aspect to look into, really to look into those digital helpers for heat pumps all along the life cycle, when it comes to planning, when it comes to integration, but also maybe when it comes to changing critical components. If certain types of compressors or frequency inverters are not available on the market, different types of heat exchanger. There are many examples that we've also seen in the last years that there are some strains also on the supply chain. So this would be an aspect to look at. Integration is a major topic. Residential, okay, placing the outdoor unit in a way that it's not impacting the neighbors and the looks of the building, but also for the industrial applications. So we have a lot of existing industrial sites, and when we integrate the heat pump, it's all about retrofitting and also finding a good space to integrate these big installations. And this is also where 3D tools can help to get a feeling of the dimensions and to find the right spot to do that. And we heard already today a lot of operation optimization. I think we are right at the beginning. So we have this research project in Aachen where they had this outlook from fault detection to predictive maintenance. I think there's a lot of more to come in this field, and it will be very interesting to continue to work in this direction.
Okay, thank you. But we can say to all the audience here that we will publish the recording and the slides, correct? On the Annex website, Veronika?
Yes.
And we will let you know when it's up there. It will take some days maybe, but we will let you know.
So I will just post the link in the chat. Okay. So it comes the link and the picture, but yeah, there you can register for tomorrow to continue these ideas and to draft this new project. We have 3 minutes left, and as we presented a lot today, and we also want to engage with you a bit, I have prepared a Menti slide. I will share my screen once again. And it's this one. So I invite you all to connect to menti.com and use the code that's written here. It's 44504034. And we would like to know what's your take-home message from today. Maybe something that was new to you, maybe something that you've already known and that was interesting to see confirmed. We can now follow this this creation of the word cloud online. So when you've connected, you can just write whatever comes to your mind as the take-home message for today, and then it will fill this space with words. Ah, yeah, so there's the proof it's working. First person is connected, first word is coming up. Okay, so we have here managing complexity. That's an important one. Simplification, good task for the future. Real applications. Yes, this was a very interesting part of our project to really see what's already out there and what kind of applications are already there. Opportunities coming. Cybersecurity, that's an important one. We haven't spent too much time on this aspect today. It is, of course, also related to connected heat pumps, but it's not only a heat pump problem in that sense. But in the task 1 report, you also find our analysis of the data security and the cybersecurity issues with an FAQ section for those who really want to work on IoT-enabled heat pumps. More answers coming. Too many protocols. There was this impressive cloud at the beginning, right? Many players cooperating. I think this is an aspect that we will find all along the energy system. When everything moves closer together, and there are many more collaborations on different aspects in the future. And yes, so with a glimpse to the time, it's already 11 o'clock. I want to thank you all for listening. I want to thank all the speakers for their great presentations and for keeping the time. Please check out the reports on the website. You will see that they contain far more details than we were able to show today. And again, I want to thank all the participants of the Annex project for the great work. And thank you all for listening. Thank you for your interest. And I look forward to meeting you again, maybe tomorrow or at some other event when it comes to heat pumps. Thank you.